In the last video, we talked about concentration as a way to describe properties of a solution. In this video, I want to look at a specific type of concentration, molarity, and it's one in a series of videos for different concentration types. As a quick refresher, the idea of concentration, it's something where we have some ratio, some relative amount of our solute to our solvent, or of our solute to our solution. In this particular case with molarity, we're going to find out that it is the amount of solute to the amount of solution. We said there's a couple common abbreviations for concentration. You may see concentration abbreviated as CONC, and you may see it abbreviated with an open bracket. And it turns out that molarity, I've dubbed the unit of choice for chemists, is so prevalent in the world of wet chemistry that when you write open brackets, it implies molarity unless you're told otherwise. So you can write that concentration implies molarity. So that's kind of interesting to note. Let's get our definition up there and we'll take a look at the components of that, and we'll look at some pros and cons. So what is molarity? It's just the moles of solute, right? Amount of our solute over the volume in liters of the solution. So it's not just the solvent, it is the solution, and we'll see some pros and cons of that specific fact in a moment here. But for right now, this is what molarity is. You abbreviate molarity as a capital M, and our generic equation would be that it is the moles of solute, and you'll commonly see me write volume in liters of the solution. Volume in liters, capital V, subscript capital L. And our units on that end up being moles per liter. All right, I'm going to box that in as our important fact here. Because if nothing else from this video, that equation is something that's going to carry over repeatedly. So as we look at this, why is it so popular for chemists to use molarity? And the first thing is, it's pretty easy math. You've only got 3 variables to work with. So pros of molarity, easy math. That's 3 variables. And I know that sounds kind of corny, but as we look at things like mole fraction or mass percent, then we see situations where the math becomes a little more complicated. Another huge pro for molarity is that there's very easy solution preparation. And in a real laboratory setting, you're going to have to make solutions with different concentrations, and it isn't always going to be professional chemists doing that mixing, and it's good if there's easy instructions. In fact, I'll write out some generic instructions that would apply to any possible molarity preparation for some solution. So, for example, we would have our instructions to prepare whatever. You're going to dissolve some amount of the solute. That could be a mass for a solid, that could be a mass or a volume for a liquid or whatever. We're going to dissolve it in our solvent. Might be water or something like that. And then we're going to dilute to whatever our target solution volume is. Using our solvent. And that is how the instructions look every single time. So in a typical situation, you'd take a volumetric flask, put some solvent in there, dump your solute in, get it stirred, dump in some more solvent until you have a total volume. So as you look at that, something becomes apparent. This doesn't say amount of solvent. This doesn't say amount of solvent because we don't know that amount. And that's a pro or a con depending on your perspective. And for the pros, I'm going to put you don't need to know the solvent amount. And on that same note, for a con, in fact, I'll start writing that con list right now, you don't know the solvent amount. And you don't need to, it just feels weird not to know it. All right, and then when we're making these solutions and we're talking about solution preparation, that's one of the things we'll address. So, something I want to point out as we're looking at our cons now is that our denominator has volume in liters of the solution, which means we're dealing with a volume, and volume changes with temperature. So, since volume changes with temperature, molarity varies with temperature. In fact, as things get warmer, volume increases and molarity goes down, and as things get cooler, volume decreases and molarity goes up. And there's a workaround for that, or a reasonable assumption related to that, which is usually labs are controlled conditions. As a little side note, it's interesting to point out if you look at glassware like even a beaker or a graduated cylinder or a Erlenmeyer flask, they have temperature ratings on them. They're calibrated to a certain amount at a specific temperature because volume does change with temperature. And the last thing I would put here is that when you're looking at the equation, you've got moles of solute in the numerator, and you don't usually measure things in moles. So you don't usually directly measure moles. And what that means is you have some extra conversion step. But in terms of raw practicality, easy math and easy solution preparation, relating directly to moles, which we can then relate directly to our stoichiometry, is incredibly powerful. I do want to put a box around this because that's a cheat sheet for any molarity you ever need to prepare.